Yeah, good afternoon from my side. Welcome to our seminar here at Fraunhofer Institute for Microsystems and Microengineering. I'm your moderator today, and my name is Michael Basler. I'm heading the Division of Diagnostics here at Fraunhofer IMM. So you have seen, of course, today's presentation is about silicon microtechnology for high precision components from prototyping to production readiness. So the procedure will be as follows. So we will have the presentation first, and then after the presentation, there will be the opportunity to ask questions via the chat function. You can, of course, type in these questions during the presentation, and I will present them in the end to Stefan Schmitt that he can answer these questions. So I just mentioned his name. So the seminar will be given by Stefan Schmitt. He is our head of group for special sensor technologies. And not to waste any more time, so let's go and start. Stefan, the screen is yours. Thank you.
Okay, thank you very much. Thank you, Michael, for the introduction. Thank you all for joining this webinar. My name, as you heard already, is Stefan Schmitt. My latest degree is I am Master of Applied Physics in Hochschule Rhein-Main in Rüsselsheim, in that case. I've been working in Fraunhofer IMM since 1998. At that time, it was called the Institute für Mikrotechnik Mainz. And I'm now project manager and head of group special sensor technology. And this is the group who is caring about manufacturing of silicon and MEMS parts in our clean room. And I will show you more about that. So what can you expect from this webinar? At first, I'll show you motivation for microtechnology. Then I will show you 3 selected success stories. These success stories are all projects which have been finalized recently or are still running. But I will not only show you the examples, I will also show you some important process steps, and I hope I can show you some things which are perhaps interesting for you to see how some processes work. And in the end, of course, I will give a short conclusion. Now, Fraunhofer IMM is one of the 75 Fraunhofer Society institutes, and there is over almost 30,000 employees of Fraunhofer in Germany. So it's the biggest research entity in Europe, as far as I know. And we are situated in Mainz, so very, very central. So you can reach us easily. Well, nowadays you can reach us by all digital means. But if you happen to come to us, you are very welcome. So in Mainz we have a staff of 140 persons, and most important is that we have made a lot of spin-offs in the area from technology we have developed. And what is interesting is that we are certified according to ISO 9001, which gives us the opportunity to have a high quality level. Now, a word to the motivation for silicon-based MEMS technology, micro and MEMS technology. Microtechnology can be found in many areas of life. And I don't mean only the normal electronics, I mean the silicon microtechnology, for instance, for accelerators and gyroscopes, for pressure sensors and microphones, and many more devices. You probably all have a mobile phone, a smartphone, and there are a lot of these devices in there. So this has gained a lot of importance in the recent 10-15 years. Now, we do MEMS technology in Fraunhofer as well. And our advantage is there that we have a resolution of a micron for mechanical devices. And that means we have a high reproducibility due to our processes, which are mainly series processes. We use these, for instance, for mechanical elements and optical components. I will show an example as my first example there. And for instance, there could be functions on the surfaces like heaters or resistors in order to measure some things. And this is also used for micro and biofluidics, as channels and sensor elements. And of course, all this is in the end more or less a sensor-related technology. Depends very much on the demands that we have. Now, before I come to the examples, just a word to our clean room and the basic process steps which are used for MEMS technology. The basis of everything is often the photolithography, because that is the chance to deposit a resist, which is then irradiated and developed. And then you can have parts where you have the resist, the parts are covered and protected by the resist, and other parts are open. Now, then you can do, for instance, a deposition and lift-off technique. For deposition, we use for thin layers, metals, oxides, nitrides, and thick layers are done by electroplating, for instance. After that, you could do an etching, for instance, with isotropic wet etching or dry etching. And you can have you can do anisotropic etching process as well. As you can see here, there is KOH etched silicon parts. But it's dry etching is available as well. And you can, in the end, you must assemble your parts. And of course, we need a lot of devices for qualification and measurement. All this is done in our clean room, which has a surface area of 750 square meters. And so we have basically 3 boxes where the processes are ongoing in a clean room area until ISO standard ISO 3. So it's a fairly clean environment, but of course not as clean as it is used in microelectronics. Let us come now first to the first example. This is a silicon-based double slit optical component for the EnMAP satellite. EnMAP, Environmental Mapping and Analysis Program, means that a satellite is scanning the Earth's surface with a resolution of 30 by 30 meters. And every of these 30 by 30 meters pixels can give us a complete spectrum from 420 nanometers to 2450 nanometers. That means that due to the fact that the spectrum range is so high, we will need 2 spectrometers to really measure this light which is emerged from the surface. And in order to have these 2 spectrometers and very precise opening, you need a certain device which defines the real view what you have for your optical components. And that is done in that case with a double slit. So 2 slits which are parallel to each other. Here is the instrument, and in here a very small part, a very important part, means that the incoming light is focused onto this double slit, and one part is going through directly into one spectrometer, and another part is going through a mirror system or an additional mirror, and then is being measured by a second spectrometer. Now the problem is here that everything needs to be very precise, very, very small. So the precision of the width of these 2 single slits is a micron. The precision of the distance is 2 microns of these slits. Then the linearity must be better than 5 microns, and the alignment of the other components, as I said, there's a mirror underneath, and there's, for instance, a baffle, and everything is glued into a INVA device. So the alignment must be better than 5 microns, which we must do by optical active alignment. Now, the trick is everything is not only on a single millimeter, everything must be obeyed at the full distance of 24 millimeters of the slit length. And the solution to get this is to use silicon microtechnology. I will show you in brief how we did this. In the left side here you have an example. That is the 2 slits, 2 openings. Only these openings here is important for your light. The rest is a mechanical structure to carry these two slits. I mean, they have to withstand the start, for instance, from the on a rocket, and so everything must be suitably ruggedized. And so what you do first is you use a wafer which is called a silicon on-insulator silicon wafer. So there's a handle layer, a silicon handle layer, there is an intermediate layer, and on top is a thin device layer, which has a thickness of 10 microns. And that you can see on the left side of the picture, that is the device layer which defines the opening, the thickness of the opening. Now you use different lithography and etching steps, that is a KOH etching in that case. And then you can you can use advanced silicon etching processes, that is a Bosch process, in order to make this vertical sidewalls. In the end, everything must be cleaned and covered with aluminum. And you can see here an example that the opening is not only vertical, it is tilted under a little angle. That means that the incoming light is only blocked at the very end of this tip here. So this is a very, and the height, I don't know whether you can read it, but the height of the slit here is 10 microns, 10.5. Now, as you have seen, we need to not only to manufacture that, it must be qualified as well, which is very important because we have space technology, we have very high standards concerning qualification, and which can be fulfilled by us. And for instance, here you have an example of the measurement of the slit width, which is the red and the black bars or black dots, which is almost perfect on the 24 micron specification. And the slit distance is even better. It's 480 microns, and there's not much deviation to be measured. And even the surface flatness was in between plus minus, so to say, 1.5 microns. That means that due to compensation methods, everything is very flat. Now the launch of the satellite will be hopefully in 2022. It's a very complex device, so it's has been postponed. But every components have been successfully tested and installed into the satellite. System testing and launch preparations are ongoing at the moment. So that is some examples from the transport containers during assembly or during delivery. And you can see here the final heart of the device. This is the slit device. And in the backside, for instance, there is a witness sample because everything has to be monitored for particle contamination issues. The most important process step is the deep silicon etching process. That is the Bosch process, which was invented by Franz Lerner and Andrea Schilp, now U1, in 1994. What they did is that they not only invented an etching, but also a deposition, a passivation process. So what happens is that you first etch a part where you have a photoresist, you etch it a little bit, then you passivate. And the trick is that the passivation is very isotropic, so it covers all the sidewalls. After that, you go for etching again, and this etching process has a little bit more influence on the vertical, on the horizontal plane. And that means the passivation will vanish quickly and will still stick on the sidewalls. And by etching and passivating with hundreds of cycles, you can get such a vertical sidewall. At the moment, we are just installing a new machine, a new silicon etcher to be on the standard again. That is an example here on the left side where we have made a micro sieve for a TEM application. And you can see here we have a sidewall of a micron and a opening of 6 microns on the sieve. And if you look very closely, you can see these horizontal lines which are due to this etching and passivation processes. The next thing is the radiation-resilient bolometer sensors for fusion experiments. Fusion energy is highly efficient. If you have like 60 milligrams of fusion fuel, tritium for instance, that can give us as much energy as 400 kilograms of coal. And ITER, which is actually built in Cadarache in France, is the biggest man-made machine at the moment. And it consists of plasma, which is confined here in a torus, which you can see here. And now what you want to have is you must control this plasma very well. And what you use for this is that you want to measure how the intensities of the plasma are at different areas or different positions in the plasma. And that has been done by Bolometers. So what you measure is the light which is emitted by the plasma. You measure that on the sidewalls. A bolometer is something like a sensor for incoming radiation, photons, which have up to 21 kilo electron volts in that case. So we need an absorber which is fairly thick. About 20 microns of gold, for instance, would do the trick. And in order to not distribute the heat too quickly to the sides, this is on a very thin membrane of 3 micron silicon nitride. And the increase of temperature is then measured by a resistor, which is made of platinum, having a good coefficient of thermal resistance. Now, of course, you can imagine that all this needs to be withstand vacuum, high temperatures, neutron radiations, and on the other side, it must be very precisely made. And the quality requirements for ITER, as it is a fusion and therefore atomic device, is very high as well. We have thought about 3 ideas to realize this. One idea is what we call the self-supporting substrate. That means we have a substrate which is very thin. It's in that case a 20 micron thick material which is called zirconia. And this zirconia material has now on one side the absorber and the other side the meanders, the measurement meanders. Or another means to go for it is silicon substrate, which is being opened and which has thin window on which a membrane is hanging with, again, absorber and meander. Or you could go for a thicker silicon plate for higher mechanical stability, but then it must be hung with flexure hinges. And that is, perhaps you remember the picture from the webinar. Okay, what we do is that we not only have one layer of platinum, but there is the blue ones here is another layer of platinum because we don't want the, we only want to have the measurement of the resistors. That is a complete wet-zone bridge. And what happens here is that one part is irradiated with the incoming light and the other part is blind. And then you have a wet-zone bridge and you can measure the distortion of this bridge. Now, how it has been done? Again, you have on one side, you have these 2 platinum depositions, and then you use a spray coating on the backside, and then you fill everything and with a photoresist. Then you irradiate it and develop this inner part. And then you can fill everything here with gold, which is done by electroplating processes. And some devices need, for instance, an additional blackening, an additional light absorbing layer for visual light, for instance, or other special functions. Now, a very new thing was to use the zirconia samples, not only the silicon, but as well zirconia thin substrates. And that is, for instance, you can see here on the left side how well this substrate bends. And that could be used for other highly temperature stable and radiation resilient substrates for other applications as well. Now, at the moment, the status is that it is successful. The 3 approaches have been successfully manufactured and they are actually under assessment. And the tests are pretty promising at the moment. So the next step is that for ITER, they will start the acquisition process in order to have a commercial contract in order to buy about 500 of these devices. And we not only manufacture these devices for ITER, but a lot of machines, of fusion machines, are equipped with our Bolometers. For instance, Wendelstein 7X in Greifswald, Aztec's upgrade in Garching, or the TCV in Lausanne. All these devices are now equipped with our Bolometers. What is a very important process step here, again, is the electroplating, because it is not easy to deposit a 20 micron thick absorber onto the backside or onto the inner side of a pit of a recess here. And we need a high reproducibility, and we need a high reproducibility not only from on a wafer, but as well from wafer to wafer. The uniformity must be very well and all these things. And therefore, we developed a dedicated process and handling system. Let me come to the last success story. That is the INFICON helium-leakage detector, Protec P3000. Now, that is the main application is leak tightness and control for industrial applications. It's, for instance, if you assemble a refrigerator, and then you fill the refrigerator with helium, and then you have a sniffing probe, which you can see here, and it sniffs whether this helium comes out. That is as well done, for instance, for the common rail injection rails, and normally a mass spectrometer is used for that. But as you perhaps know, a mass spectrometer is a very precise device which needs high vacuum requirements, turbo pump, and all these things. And you don't really want to have this in an environment where you have manufacturing, industrial manufacturing. So this device works differently. I will show you on the next slide. And the system has been developed by IMM and INFICON in Cologne. And it's they're very successful on the market since 2005. And this WISE technology and the way to produce this has been developed by us. Now, what is the specialty about this detector? It works with a pressure gauge, which has a window on the front side, a membrane which only lets helium permeate. So as soon as you sniff in air which has a certain content of helium, this will be able to go through the membrane and increase the pressure in the pressure gauge, which is normally very well evacuated. And that by only measuring this pressure increase, you can directly measure the content of helium. And that has been done by a silicon oxide membrane, which is spun over silicon support with the heater. You can see here the heater meanders. And the system, as I said, is on the market since 2005. And we have additional detection systems for different applications. And we make further developments, which are constantly ongoing. And as this is now being manufactured by us since 2005, you can imagine that we have a very high level of quality, including very good customer satisfaction. And it's very important for us that we know not only how to manufacture something for the first time, but to do a reproduction of it as well. Just a moment, please. Now, again, one of the most important processes, apart from the silicon etching, is the platinum resistors. What we do here, we have a very special photoresist, which has a step. And you first deposit this photoresist and open it. And then you deposit the platinum. And then you make a lift-off process. So everything which has the resist underneath has been washed away, and only the platinum is remaining. That is very important, because you cannot really very well etch platinum. And what we do here is 100% test for our customer, so that he really can use it without any additional tests. He just opens the box and uses our devices. Now for the conclusions for microtechnology. The silicon-based microtechnology is a key technique for applications with a higher requirement for mechanical precision, temperature, sometimes chemical or radiation resilience, high reproducibility, and the realization of very specific functionalities. Now, often people come to us and we make a contract research. That means we do a development, a realization or provision of components and plants. We can make only a special process development for piloting or production. And what we have done already as well is that we have developed things and transferred it to other the technologies into the products, and let our partners do the manufacturing later on. And of course, we are open for consulting, education, staff training. And of course, we not only do a contract research with industrial partners, but also we engage in public funded projects, either national or international. Okay, so that's everything from my side for today. Thank you for your time, and now we are open for questions.
Yeah, thank you, Stefan, for your very nice presentation and for these 3 really interesting examples. So I have already collected a number of questions. So please, of course, feel free to type in additional questions in the meantime when we will start to talk about the questions I have already collected. So the first one is, I read it here. These seem to be quite complex projects with impressive results. Can you talk about the duration of these projects, Stefan?
Yeah, you're completely right. This is, I mean, these are the most interesting processes or projects. So, which I have chosen because it shows so many facets of what is possible. But often the requirements are much lower. So, for instance, we have often done interdigitated electrodes for different measurement applications, which are on glass or on other substrates. We have done only what we do regularly is only a deposition of a gold layer for another company, for instance, or other very easy approaches. What is important for me is that I always try to find out what is really the demand or the requirement of a customer, and try to choose the process which is most successful for it. And that doesn't necessarily mean that it's the most fancy processes. Sometimes it's an easy process is better.
Okay, so but you didn't now answer the question.
Oh, yes.
These projects really took.
I'm sorry. Yes, yeah. I was only thinking because now you can imagine the processes have been running since one project has been running since 2005. That is on one side of the scale. But for instance, we have just done something for the fair project, which is
facility, yeah.
Fair facility, yes, and that is something where we have processes which are more common to us and which we have already mostly developed, and that takes about, let's say, 8 to 12 weeks. But also, if you come and want just a single digitated electrodes, we're able to provide that within 2 or 3 weeks' time. So that's a very large span.
Okay, thanks to that, Stefan. So the next question here is a little bit similar, sort of. So how were these projects funded? So you didn't talk about this.
Yeah, that's true. That's in that case interesting because it's very different fundings. This leak detector project is completely funded by industry, by INFICON in that case. They are very proud that they have a very deep intensity of manufacturing, and so they want to possess the processes. The Bolometers, they have been funded by very different means. Sometimes it was a public funded project from the state, from Germany. I don't know whether it was a scientific ministry, where we were a subcontractor. And now we are in a consortium together with IPP in Garching, Max Planck Institute. Here we have a kind of a EU-funded project, and the Double Slit is funded in the end by DLR, and the prime here in that case is OHB. So very differently.
Mm-hmm. Okay, so then a question again to this. So in the end, you alluded a little bit to that, but the question here is now, how does it work to start a project with you as a company approaching you?
This is very, very different. Normally what happens is that people drop in with an email, mostly made by the web front end, and then what I'd always try to find out is what is the real requirement. So what we do in the end, we make a requirements list and compile everything so that in the end a contract is very clear for both sides, that everyone knows what to do and how to do it. But it depends very much on the requirement and what has to be done. It could be, for instance, a fixed sum, or it could be, for instance, that we work on an hourly basis. That is very dependent on the project.
Okay, thank you. Then there's a technical question here for the double slit.
Yeah.
So what are the methods to measure the precision of the device over this large size?
It's a good question. I didn't want to talk about that because it is. You can imagine that we are now talking about. Well, that picture was, I think, good. Now, this is something which is hard to measure with light, but the problem is that in the end, light is being used in order to at this position. So we don't measure it with SEM or other methods. We really use it with an automated measuring machine with a where you have a projection of the light. But what we do is that we had some slits which have been calibrated by PTB, and so we can put that back to certified standards by using these slits which have been qualified by PTB, so that we always know that our machine is measuring according to the standards. I hope that answers the question.
I hope so, yes. So then there's okay, no, if you have something to add, of course.
No, in general, it's a video camera system, very high resolution microscopic video camera system, where we measure it with light.
Yeah, but the key message is really that there's a calibration standard available.
Yes.
And then a high precision instrumentation specific for that slit, right? Yeah. Okay, then the other technical question I have here is, you talked about, this is obviously for the bolometer, you talked about photons with 21 keV. So what is the spectral response of the bolometer is the question.
Yeah, there's two responses. I mean, one is the voltage response, but the problem is that the incidents are sometimes very, very short. So we're talking about incidence times of some hundreds or some tens of milliseconds. So the bolometer must react very quickly. And now that is the reason why I cannot really answer the question, because some bolometers have been optimized to react very quickly to low incident radiations, and therefore you need a smaller absorber layer, and others have been for higher radiations, and then you need a larger absorption layer. But what is measured in the electronics from IPP in Garching, for instance, is something like tenths of degrees Celsius or tenths of Kelvin. So a tenth, so it's like 0.1 Kelvin difference when an incident is coming.
So what you're talking about is the NETD, right? So, but I read the question about the spectral response. So what is the spectrum that is really collected?
No, there's no spectral response. It's covering the complete spectrum from visual light to high energy photons.
Okay, so those are the questions I have collected here. So let's wait a second if there's any more question. I don't see any reaction. So then, to my point of view, we can close the session for today. So there's of course the possibility to contact Stefan directly, as he said, via the web page, for example, and you can contact us via this this webinar tool and via, of course, the way you applied, or better you registered for this webinar. So you will find us on our website. Stefan will be available for any question today or any other day you want. So there's one question. Ah, yeah. He mentioned here, a person from the communication teams, that the email address is events@immfraunhofer.de, where you can directly contact our communication teams, and they will forward the information to Stefan Schmitt. So there has not been any further questions so far. So thank you for your attendance, and I hope we will see some of you back on the next online seminar, which will be in a few weeks and will be announced again on our website. So thank you again, and bye-bye.
Have a good time, have a good day, and stay healthy. Bye-bye.
So.